The four forces that act on an airplane are lift, weight, thrust, and drag. Whenever there's an imbalance between lift and weight, the airplane will either climb or descend. Whenever there's an imbalance between thrust and drag, the airplane will either accelerate or decelerate. When opposing forces are equal, the airplane is in steady state, unaccelerated flight. So when lift equals weight, the airplane is at a constant altitude, and when thrust equals drag, the airplane is at a constant airspeed. So we're going to talk about all of these forces, but let's start with lift. In order to really properly visualize lift, we just have to go over some very basic physics. First thing we need to understand is that air is a fluid, just like water is. A lot of times when people try to visualize airflow, they think of these independently moving particles that ricochet off things or bounce off things by themselves, but that's not how air behaves. That's not how a fluid behaves. A fluid can either be a liquid or a gas. Air is a fluid and flows together as a whole, just like water does. So you could think of it just like how all the oceans and rivers sit on top of the Earth's surface and flow together as a whole. The atmosphere does the same thing. The atmosphere is just a layer of fluid that's sitting on top of the Earth's surface. So fluid flow can either be smooth, ordered, and layered, which is called laminar flow, or it can be rough, disorganized, and irregular, which is called turbulent flow. And it's this laminar flow that we need to produce a force. So laminar flow is what's going to be useful for us. Turbulent flow isn't really useful for us in any sort of meaningful way. We need laminar flow to produce a force. Okay, so this is a Venturi tube. A Venturi tube is just a device that's narrowed in the middle like this, designed to speed up the flow of a fluid. So when a fluid flows through a Venturi tube like this, two laws of physics that it must obey are conservation of mass, which just says that mass cannot be created or destroyed, right, obviously, and the continuity equation, which just says that the input rate must always equal the output rate. So let's say, for example, the fluid is flowing through this Venturi tube at 20 gallons per minute. Okay, so we need to move the same amount of fluid in the larger portion through the narrower portion while maintaining that 20 gallons per minute. We can't change the flow rate. So if we assume that this fluid is incompressible, in other words, we can't pack it into a smaller space, the density can't change, then the only way to move the same amount of fluid in the larger portion through the narrower portion at 20 gallons per minute still is to speed it up. So that fluid has to speed up in order to obey those laws of physics. Now, an increase in speed is considered an increase in energy, and you can't just increase energy without taking it from somewhere else. We have to borrow that energy from somewhere. So it gets borrowed from the fluid's pressure. So as the speed of a fluid increases, the total amount of energy in the system has to remain the same. So as the speed of a fluid increases, its pressure must decrease, so that the total amount of energy in the system remains the same. And then conversely, as the speed of a pressure decreases, we can't just destroy that energy. That energy has to get returned in the form of pressure so that the total amount of energy remains the same. This is referred to as Bernoullis Principle. So Daniel Bernoulli was a mathematician in the 1700s. He published a work called Hydrodynamica, which was basically a work on fluid dynamics, and he pioneered this idea. He was the first one to sort of investigate this relationship, that the faster a fluid moves, the lower its pressure, and the slower a fluid moves, the higher its pressure. So this is a pretty general and simple relationship, but it's big for the FAA, so the FAA definitely wants you to know it, so it's definitely important to commit this to memory. Okay, an airfoil is anything that's designed to manipulate the flow of air to produce lift. The ideal shape depends on how fast and at what altitude it's going to be flown at, but they all are shaped to manipulate the flow of air to produce a force. Okay, airplanes move in three dimensions. We can control pitch, roll, and yaw, so they move around three axes. The lateral axis, which extends from wingtip to wingtip. The vertical axis, which extends up through the middle. And then the longitudinal axis, which extends from the nose through to the tail. Okay, now let's just talk about some basic airfoil terms. We have the upper surface, the lower surface, the leading edge, the trailing edge. The chord line is just an imaginary line that gets drawn from the trailing edge through the leading edge. The relative wind is just the airflow as it passes over the airfoil. Whatever direction the airflow is coming from and passing over the airfoil, that's the relative wind. Now, the angle formed between the relative wind and the chord line is the angle of attack, and we can change the angle of attack by pitching up and down. The angle of incidence is essentially the angle at which the airfoil is attached to the fuselage. This we cannot change. This is a fixed design feature of the airplane. It's just the angle between the chord line and the line parallel to the longitudinal axis. The camber is basically the shape or the curvature of the airfoil. This is arguably the most important design feature, as we'll see in just a second. But first, let's talk about what happens when the air flows past the airfoil. So air has a certain degree of viscosity. Viscosity is just basically the thickness of a fluid. So fluids flow in layers, and viscosity is basically the friction between those layers. So the more viscous something is, the more it resists free flow. So things that are examples of fluids that are very viscous would be like oil or honey or grease. They resist free flow. They're very viscous. The less viscous something is, the more freely it flows. So no surface on Earth is perfectly smooth. If we look close at anything, we'll be able to see these tiny little imperfections in the surface of the skin. So as the air flows past the airfoil, the air the layer of air that flows just above the surface gets caught in these tiny little imperfections and sort of stagnates here. Now, because of the viscosity of the air, because of the friction between layers, this area of stagnation right here sort of drags down the layer that's flowing right above it. And then again, because of the viscosity of the air, the layer that flows just above that one gets dragged down a little bit and slowed down a little bit, and so on, until we have smooth laminar flow. So we have this area of stagnation that gradually increases to smooth laminar flow. That area of stagnation is called the boundary layer. Now, because of the viscosity of the air, because of the friction sort of dragging the airflow downward, the friction of this slower moving stagnating air, the air follows the boundary layer. Now, the boundary layer is usually very thin. It's usually no thicker than like the thickness of a credit card, but it can change. And the important thing to understand here is that because air follows the boundary layer is what forms the effective shape of the airfoil. Now, if you're with me so far, you're thinking, okay, well then it doesn't really matter what the actual physical shape of the airfoil is. All that matters is the shape of the boundary layer, because that's what the smooth laminar flow is going to follow. And that's correct. Smooth laminar flow is what we need to produce a force. Okay, so airfoils create lift in two ways. The first way is by directing the airflow downward and then reacting against that downward flow. So let's look at a symmetrical airfoil. So when a symmetrical airfoil is at a zero angle of attack, the airflow will pass over the upper surface and under the lower surface in the exact same way. Whatever happens to the flow above the upper surface is going to happen in the exact same way to the flow underneath the lower surface. So generally, airfoils are not designed like this. Generally, the upper surface is rounded and the lower surface is flatter. So remember we said that the boundary layer just above the surface is usually pretty thin. Okay, since air follows the boundary layer, the smooth laminar flow follows the downward slope of the airfoil. Okay, so the wing is basically directing the airflow downward. The wing is exerting a downward force on the airflow. Now, Newton's third law says that every action has an equal and opposite reaction. So this downward force has an equal and opposite upward force. Okay, now it's not like the air particles are, like bullets being shot out of a gun and are bouncing off or ricocheting off the bottom, the lower surface of the airfoil and pushing the airflow up. Remember, that's not how a fluid behaves, right? A fluid flows together, and so the airflow gets directed downward, and then that downward direction has an equal and opposite upward reaction. So we're basically just reacting against the air. We're pushing it downward, and by pushing it downward, we push ourselves up. So that's the first way that airfoils produce lift. The second way that airfoils produce lift is they create a pressure differential. So like we said, generally the upper surface of the wing is rounded and the lower surface is flatter. So as the wing moves through the air that moves up and over the upper surface sort of gets pinched. It sort of gets squeezed. And because it gets squeezed, it has to speed up, just as we know from looking at our Venturi tube. When a fluid speeds up, its pressure decreases because of Bernoullis Principle and conservation of energy. So what winds up happening is we have this area of lower relative pressure formed just above the upper surface. So lower relative pressure meaning lower than everywhere else surrounding it. So the air underneath the wing is at a higher relative pressure than the air over the upper surface of the wing. High pressure always pushes towards low pressure, and that produces lift. So before we go any further, it's important to understand that this is an extremely complicated mathematical topic. So this explanation is very general. The only way to completely explain this is to demonstrate it with equations, is to demonstrate it mathematically. We're basically trying to visualize what happens to the flow of air over the upper surface when what we should be doing is plugging the conditions into different equations and explaining it that way. This is just a topic that's best explained using numbers instead of words, but that's okay because we don't have to get that deep into it. For our purposes, we just want us to understand the general principles. So all we want to take away from this is that the airflow over the upper surface speeds up, generally because of the shape of the wing. Because it speeds up, its pressure decreases. So we create an area of lower relative pressure above the wing. So we have higher pressure below that pushes up towards that lower relative pressure. One of the really cool things is under the right conditions, we can actually see this area of low pressure being formed over the upper surface of the wing. This is because of something called the Classiest Club relation, and it just causes fluids at low pressures to undergo a phase change and condense. But we can actually see this happening in real life, which is pretty cool. You don't have to know this. It's just interesting to actually see it happening. So to create lift, all we need to do is change the way the air flows past the airfoil. And it's the shape of the airfoil that does that. It's the shape of the airfoil that directs the airflow downward so that the airfoil can react against that downward force and create lift. It's the shape of the airfoil that sort of pinches the airflow as it passes over the upper surface, so it has to speed up, creating an area of low pressure above the wing. It's the shape of the airfoil that changes the way the airflow behaves. And all we need to do to produce a force is to change the way the airflow behaves. So let's go back to our example of a symmetrical airfoil. Remember we said that a symmetrical airfoil at a zero angle of attack, the air will pass over the top and underneath the bottom in the exact same way. So whatever happens to the airflow over the upper surface will happen to the airflow underneath the lower surface. There'll be no net difference. There'll be no force imparted on the airfoil. Now, if we increase the angle of attack, that will change the way that the airflow passes the airfoil, and that will direct the airflow downward. So now the airfoil can react against that downward force that it's imparting on the airflow, and it'll produce lift. It'll also sort of pinch the airflow as it passes over the upper surface. That airflow will have to speed up. There'll be an area of lower pressure created over the top of the wing. By the way, look at our boundary layer right here. Okay, let's look at what's the effective shape of the airfoil. Remember we said the boundary layer forms the effective shape of the airfoil, and the effective shape of the airfoil is what that smooth laminar flow follows. That's all that matters, and that the effective shape of our airfoil looks a lot like that traditional airfoil shape right now. Now, let's take this a step further. What about just a flat board? Well, at the right angle of attack, it can change the way that the air flows, and it can direct the airflow downward, and the flat board will react against that downward flow that it imparts on the air. And it'll also sort of squeeze the airflow as it passes over the upper surface. That airflow will speed up, and an area of low pressure will be created over the top. Now again, let's look at the boundary layer. Why does the smooth laminar flow get directed downward? Because it follows the boundary layer. Why does it follow the boundary layer? Because of viscosity, because of the friction in between these two layers. The friction in between these two layers sort of drags the airflow downward. So we import a downward force, and we can create lift. So all we need to do to create lift is to change the way the air flows. Airfoils are just shaped to do this in an efficient way. In theory, if we attach two giant boards to the sides of an airplane, they could create enough lift to overcome the weight of the airplane. They would just have to be so gigantic, and it would just not be practical or feasible in any realistic way. But the point that I'm trying to get across here is any shape can produce lift as long as it can manipulate the flow of air. So like a baseball can create lift. That's how pitchers throw curveballs, is they put a certain spin on the ball. That spin manipulates the flow of air. It creates lift just in a downward direction, and the ball breaks away from the batter. So anything that can manipulate the flow of air can create lift. So naturally, the greater this downward force, the greater the equal and opposite upward force is going to be. So if we increase the angle of attack, we steepen the angle at which the air gets directed downward. And so we increase the downward force that we exert on the airflow. So that results in a greater equal and opposite upward force. Additionally, the greater our angle of attack, the more the airflow over the upper surface sort of gets pinched. So it has to move even faster. Even faster airflow means even lower pressure, and that increases the pressure differential. So now the difference between the high pressure underneath the wing and the low pressure above the wing is even greater, so that's going to result in a greater upward force. So as our angle of attack increases, our lift increases up until a certain point, and that's called the critical angle of attack, but we'll cover that later. So if we increase airspeed, that means the force at which the air gets directed downward is even greater. Okay, this results in an even greater equal and opposite upward force. So the more forcefully the wing directs the air downward, the more forcefully it reacts against that downward deflection and pushes itself up. Simultaneously, at a higher airspeed, the air is going to accelerate up and over the upper surface even faster, which results in even lower pressure. That means a greater pressure differential. So that means a greater difference in the lower pressure above the wing and the higher pressure below. Greater pressure differential means greater amount of lift. So as we increase airspeed, lift also increases. So if we look at the total upward acting force on the airfoil, the average center of that upward acting force is called the center of lift. So you could think about it like this. If we had to pick one point through which all the lift is focused and is pushing upwards on the airfoil, it would be the center of lift. So it's just the mathematical average of the lift that's acting on the wing. It's the mathematical center. The FAA sometimes refers to this as the center of pressure. Now, if we change the angle of attack and change the way the lift is distributed around the wing, naturally the center of lift is going to change, it's going to move. So generally, if we increase angle of attack and increase the amount of lift, center of lift is going to move forward. And then generally, if we decrease angle of attack and decrease the amount of lift, center of lift is going to move backwards. Okay, now since this is a complicated topic, I think it's a good idea to go over some commonly given but very incorrect explanations. So the first one is the equal transit time theory. So some people, the way they explain this is the way they account for the air moving faster over the upper surface is by saying that when the air particles diverge and some go over the upper surface and some go over the lower surface, they're forced to meet up at the same point at the trailing edge of the airfoil. So because they're forced to meet up at the same point at the trailing edge of the airfoil, and since there's a greater distance to travel over the upper surface, therefore the air that moves over the upper surface has to move faster in order to meet up with the air moving over the lower surface. This is completely wrong. What I hope are some obvious reasons. First of all, the natural question to ask would be why? Why do these particles or these air molecules have to meet up at the end? The answer is they do not. Not only do they not have to, but they don't. If you look at any wind tunnel test or mathematical simulation, the air that moves over the upper surface gets past the airfoil before the air that's moving underneath the lower surface. So the air particles do not meet up at the end, and I don't really know why this is even out there, to be honest. But I've even seen this in certain test prep books, which I'm quite surprised about. But this is completely wrong. It does not move faster. The air does not move faster over the upper surface because it has a greater distance to travel, because there's no reason that these air particles have to meet up at the end, and these air particles do not meet up at the end, in fact. So this is wrong, and it's easily disproven by looking at any wind tunnel test. You could just go on YouTube. Please do not let anyone tell you this. The second one is the skipping stone theory, we can call it. And this is more of an incorrect application of Newton's third law. Newton's third law, of course, says that every action has an equal and opposite reaction. Okay, so basically the way people explain this is that when the air ricochets off the bottom of the airfoil, and when it ricochets, there's an equal and opposite upward reaction. So the air sort of pushes the airfoil up. And that's not how a fluid behaves. Remember, we said that a fluid flows together as a whole. So it's not, the air particles are not ricocheting off the bottom. They're being directed downward, and that downward direction has an equal and opposite upward reaction. Okay, so let's just do a quick recap of what we've talked about so far. Air is a fluid. When a fluid speeds up, its pressure decreases because of conservation of energy. That's Bernoullis Principle. Because of the shape of the airfoil, the airflow moving over the upper surface speeds up, which creates an area of low pressure above the wing. Because we have higher relative pressure below the wing, that higher relative pressure pushes the wing up. Newton's third law says that every action has an equal and opposite reaction. So, because the air follows the boundary layer downward, gets directed downward, and has an equal and opposite reaction upward. So, both of those things contribute to lift. So we could say that lift is created by just changing how the air flows. The more we increase the angle of attack, the more we increase lift, because we increase the effects of both Newton's third law and that area of low pressure. So we increase the pressure differential, and we increase the extent to which the air gets directed downward. So both of those forces increase, so we increase lift with an increase in angle of attack. An increase in airspeed also increases lift for the same reason. We're increasing both of those factors that create lift. The air moves past the airfoil even faster, so it means it moves up and over the upper surface even faster. That air accelerates up and over the upper surface even more, so there's an even greater pressure differential. The air that gets directed downward gets directed downward more forcefully, so there's a more forceful equal and opposite upward reaction. So the center of lift or the center of pressure both mean the same thing. It's just the average center of all those upward forces. So if we were to pick one point that all the lift centers on, and we would be pushing the airfoil up, it would be the center of lift. And as angle of attack increases, the center of lift, or the center of pressure, which is also called, will move forward because of the way the lift is distributed above the wing. As the angle of attack decreases, the center of lift moves rearward.